been generally interested in the coevolution of host symbiont associations and specifically Drosophila Wolbachia associations. I hope I can get you excited about Wolbachia in the next few minutes. So what are they? Well, they're intracellular alpha proteobacteria that infect the majority of terrestrial arthropods on the planet. They're maternally transmitted, so they should co-evolve towards mutualism, despite this being a host parasite session. They're classically famous for reproductive manipulations that include male killing, where you can get distorted sex ratios, and cytoplasmic incompatibility, which is this effect where you get an infected male crossed to an uninfected female. You get reduced egg hatch rates relative to the reciprocal cross. And if you saw the dengue session yesterday with Michael Trelli and others, you'll know that they're now being used to stop the spread of vector-borne disease, including dengue fever. So when you take Wolbachia labeled in green here out of melanogaster and you put it into Aedes aegypti, which normally doesn't have it, they no longer pass on dengue fever. And that's a more complicated story that they talked about yesterday. But our big question is, what's going on with Wolbachia? So what's the origin and how are they maintained? Well, for CI systems like our lab's worked on for 3 decades, you basically just need to know 3 things. So what is the fecundity of infected individuals relative to uninfected individuals? What is the fidelity of maternal transmission? So if I'm infected, with what fidelity do I pass that on to my offspring? And then what are the hatch rates of uninfected eggs fertilized by infected males? This leads to some pretty nice predictions. So if Wolbachia increases host fecundity, it can spread from low frequency, 0 becomes unstable. Alternatively, if it's depending on CI, where you don't have this fecundity enhancement at low frequencies, what you get are these bistable dynamics, and that's what they see in the mosquitoes they talked about yesterday in the dengue session. Essentially what this means is that you have stable equilibria at 0 and at some higher frequency. In words, you basically need a lot of males in the population that are infected to go out and mate with uninfected females to effectively reduce their fitness relative to infected genotypes. Now we're working on this in a number of systems in the melanogaster group, but today I'm going to talk to you about these 3 hybridizing species, Drosophila eucuba, Santomea, and Tiesieri. They're within the melanogaster subgroup. Santomea is the most recently discovered species in this subgroup in around the year 2000, and it's endemic to this island, Sao Tome, Africa, which I'm showing you here. So Drosophila eucuba can be found at low elevations on Sao Tome. Santomea is at high elevations with a hybrid zone at about 1,000 meters where you can collect F1s if we were to put out traps there. If you jump over to Bioko, so we're on the west coast of Africa here, if you jump over to Equatorial Guinea, eucuba is again at low elevations, but now you have Tiesieri at high elevations. I should mention these 2 species also occur in continental Africa. Now, what's cool about these is that they do hybridize. A nice paper from Doris Bachtrag in 2006 suggested that we have lots of, what I want you to see here is based on these pairwise comparisons, we have lots of nuclear divergence, but no real cytoplasmic divergence. And that makes sense. So you get this hybridization and then back crossing into each species. And so these cytoplasms are bouncing around across species boundaries. So we know we can collect Eucuba Santomea hybrids on the island of Sao Tome, but we hadn't collected the Tiesieri ones on Equatorial Guinea. David Turricini and Daniel Matute's lab has a nice paper that came out this year in the Journal of Evolutionary Biology, where they show these are the pure species crosses, so Tiesieri, Santomea, and Eucuba. These are all other possible crosses. The point is they showed empirically that you can get fertile F1 females and sterile males in all possible between species crosses. And again, that matches the genomic data that we've seen. So what about Wolbachia? Well, all species, these are based on limited surveys, all species are infected with this WAU variant that we find in simulants, or the similar variant that is found in simulants. Based on limited surveys, we see infection frequencies are from 10% in Eucuba all the way up to almost every line that's ever been assessed in Drosophila tiesieri being infected. These are very limited surveys, so we grab all the lines we have and we assess them regardless of where they come from. The variant's been shown to not cause cytoplasmic incompatibility, and no fitness effects have been observed. So these different infection frequencies out in nature, we really have no idea what Wolbachia are doing or why they're there in this system. Okay. So I've been evaluating what's going on with Wolbachia for time. So we have collections over the last decade or so. And then among these islands that I mentioned, so what's going on in infection frequencies through space, and what are the fitness effects that maintain these? So So the first thing we do is we use these typing loci to verify that they all have the same Wolbachia like previous people have shown. One caveat here, of course, is that we can only see what we can see. We need a whole genome, so there could be variation outside of these, but for our purposes, on average, all of the data that we have suggests that the same Wolbachia on average is infecting all of these species in all the populations. We've looked at all of our populations. So how are infection frequencies changing through time and space? Well, now we're looking at this island of Bioko. And what we see in Drosophila eucuba is that in 2009, it was only at 3%, and it's increasing to 20% in 2013. It's a similar story in Drosophila tseri, except they're at higher frequencies. In 2009, it was at 48%, and then up to 67% in 2013. We jump over to Sao Tome. What we see are infection frequencies. This is the one with eucuba where we have an earlier population collection. What we see are 40% in 2001 were infected, and that's all the way up to 80% in 2009. So these infection frequencies are increasing. I should mention that this one is statistically significant. The last one and this one here are not, but the trend is generally the same. They're increasing in frequency through time. I just got back in February from Sao Tome, so we'll have a new data point for 2015 for both of these. And presumably if this is still increasing, we can get a better comparison. This is only over the period of 4 years here. Spatial variation. So in 2009, we have collections from both of these islands, Bioko and Sao Tome. And what we see is that on Bioko, only 3% of individuals were infected. You jump over to the island of Sao Tome, and it's up near 80%. So remember, again, these are on average the same Wolbachia, but we see these drastically different infection frequencies through time and space. Okay, so remember I told you there's those important factors for determining the spread and maintenance of Wolbachia, and so we're interested in how they impact host fitness. Well, when we look at host fecundity, what we see is that there's no effect of Wolbachia on host fecundity. So for everything I'm going to show you, we do reciprocal crosses. So we have the infected male and infected female. We reciprocally cross those uninfected genotypes. We do this across the population. So we're looking for any particular crosses that might show us something interesting. And again, what we see is over this period of 5-day egg lays, no difference. There's also no difference in egg hatch rate, so any component of fitness we've looked at relative or related to fecundity has not shown us anything. The same is true for cytoplasmic incompatibility. So we do the reciprocal cross here. Again, we're scanning across the population, so these are 20 to 30 independent reciprocal crosses. What we see is that the putatively incompatible cross, which is infected male by uninfected female, labeled as IC here, does not have reduced egg hatch rates relative to the putatively compatible cross for any of the 3 species. So this supports what we saw in the past, or others saw in the past, that there's no CI in the system. Now, however, the reason I did this across the population was to say, okay, well, let's assume maybe some crosses will generate it. Maybe it's not like simulants where every infected individual cross to every uninfected individual gives you CI. And we indeed see that. So in Drosophila tseri, there's one interesting cross 71. When we go in and then I highly replicate that 20 to 30 times, what we see is that there's a 25% reduction in egg hatch rates for this cross reliably. Okay. So now remember, I told you on average they all have the same Wolbachia. So then a question was, well, let's just assume that they do. Let's put this in different nuclear backgrounds and see if it persists. Is this the Wolbachia or is there some interaction? And when we do that, what we see is, so what I show you here is if we back cross for 4 generations into 2 different nuclear backgrounds, and then we do the reciprocal cross with the original uninfected line from cross 71. So everything is controlled here except the nuclear background with that Wolbachia that induced CI in cross 71 was placed in. Now I'm just showing you cross 71, the same data I've already shown you here. This is back cross 1 and back cross 2. So we now have the Wolbachia in a different nuclear background. We complete that reciprocal cross with the original uninfected line. And what we see is that this effect goes away. So the putatively incompatible cross has slightly higher egg hatch rates, the putatively compatible has slightly lower, and it's not statistically significant anymore. And we see this in all the backgrounds we back cross it into, it goes away. So the next thing we were interested in is thinking about the genetics of this interaction. So we see that we get CI in this cross 71. It goes away in the nuclear background. So we thought, okay, let's do let's do the reciprocal cross, get the F1 individuals, and then repeat the reciprocal to the original uninfected line to see if it persists in the F1 process, to try and get at the genetics of this nuclear interaction that we're seeing. And when we do that, what we see is, and I'm showing you here, we get those infected F1s, male and female. We reciprocally cross those to that original uninfected line. And what we see is that that 25% reduction in ACAT rate is no longer there, but it's still highly significant. It's just it's 10% now. So this is persisting in F1s, suggesting some degree of dominance. And we're hoping to get more of this. We have additional process set up to see if that works in other ways. Okay. So conclusions, the hybridization has led to these cytoplasms bouncing around across species boundaries. The frequency of Wolbachia infections are generally increasing through time. In Drosophila eucuba, we see that this is significant between 2001 and 2009. The strength of CI appears to segregate within natural populations, which is a new finding for us. So in the past, you take an infected line and an uninfected line, you pick any of them, you cross them, you get CI or you don't, and that's just the way it works in that system. So this appears to be fundamentally different, and that's, we think, because it's interacting with the nuclear background. And interestingly, when we do find it, it persists in F1 offspring. The last thing I'll leave you with is that we think these reproductive manipulations are really cool that we see, like CI, but the fact is that that could never make 0 unstable. It's a frequency-dependent thing, so you need lots of males in the population for CI to matter at all. And so in this system or any other system of CI, we have no idea how Wolbachia is spread. No idea. We go out and we sample them at high frequency, they're there, we see CI, that's great, but we don't know how they got past that upper equilibrium. So with that, I'd like to thank Michael, his amazing mentor. Paul Ginsberg's our tech, but he's more than that. He's applying to grad school. If you see this name in your application file, he's amazing. And he's very, very well trained. Daniel Matute and David Turner Sr., who I travel with to Africa. I'd like to thank the guides and local communities because they're just amazing people and they let us come in and use their biological material to answer these questions. I'd like to thank everyone in our lab, the third floor of Storer Hall. If you haven't been there, you should be. It's amazing. And the NIH for the money that they've given us to do this stuff, which has been wonderful. And I'll leave you in the hybrid zone on Sao Tome. So if we were to put a trap out here at 1,000 meters in Sao Tome, we could collect F1 hybrids from San Tome and Yucua. It's a pretty cool place. Okay, any questions? I have time for a couple questions. Yeah.
Do you think there's also genetic variation in the susceptibility of the uninfecteds? And also, have you looked at all the environmental variation in that?
Yeah, no, so we haven't. I think there very may well be. So what I did do is when we were in Sao Tome in February, we collected an altitudinal climb, with the idea being that these are changing through time and space. If it is very environmentally dependent, maybe we can see a difference in these infection frequencies as you go up from Yucuba into the hybrid zone up through San Tome. So we have 30 lines, 30 lines, 30 lines, all the way down that through the hybrid zone. And so those will be in the lab hopefully next week or the week after to look at that. But I absolutely think it's environmentally dependent, but no idea how. Any others?